Hello, everybody. In this lecture, we will continue from the previous lecture. So far in your let me remove that. Yes, delete. So far we have gotten our data set inside. We have imported it in X Enterprise Miner. We explored it. We played around with it. We saw if there was something wrong, or I'm sorry, I shouldn't say something wrong. Uh, we were trying to understand the data, as well as we were trying to understand what the data was all about. And our question we were trying to answer was whether we should uh, approach somebody who in the past has donated money to us. Should we approach them again to donate money to us or not, based on some data collection we have done? So we were basically doing these two steps: understanding the data and what the problem is. Then we did the replacement, which you can say was part of data preparation, where we find out that around 25% of our data set had income of people, zero as reported. And I don't want to say all the 25% was giving money to us, because we have both 0 and 1, being predicted in our data set. So but at least that would have impacted our final result. So to fix that, again, we have already done this. We replaced all the zeros for the medium income to missing values, so that we know what to do. And then as a next step, where is now data partition? Right there. Next step we do is data partition, which you would have already done for your assignment number 1, decision trees. And in this case, we are just going to divide the data 50-50. And yes, so you have 3 options: training, validation, test. So let me first go back here just to remind you. So we have already covered all this. Whenever I come back to the slides, we have already covered this, but I just want to tie this up with our our practical work which we are doing right now. So whenever you have any algorithm, decision trees, a neural network, or regression, whatever you want to do, you split your data. And generally as we have talked earlier, you split it into the training data and testing data. So for example, first I will split my, let's say I split my data into this 50%, so that my algorithm, whether it's regression or decision trees, it can learn from this. So what it will do is it will say, okay, if overcast, this temperature, humidity, and windy, that means play is yes. So it will learn from the model. Once with this data set it has learned, then it used the testing data set, the second part, this one, the rest of the data which we have, to test whether our algorithm is good or not. So for example, in this case, what I will do is I will use this data set like that, and whatever model, regression, or decision tree I've developed, I'll ask my now my trained algorithm, make a prediction. Can I play outside? If it says no, that would mean that the answer was no, and we also predicted as no. So good prediction. We are doing fine. In second scenario, again, the answer is no. If let's say we predict yes, that means the answer was no. We said yes. So false positive. Then if the answer is yes and we also say, sorry, if the our data mining program regression decision tree says yes, and the real answer is also yes, because this is a past data, yes and yes, true positive, oh, we are accurate. And if the real answer was yes, but our algorithm said no, that means it's false negative. Okay. So that is how you measure the accuracy, positive rate and true negative rate for your model. So that's why we need to keep a good amount of data set to test our model, so that we can see how good of a model we have developed. Uh, Once you have created a algorithm, data mining algorithm, based on your training data set, you cannot just release it in the industry and say, hey, it's ready to use, go and use it. They want to ask you, what's your accuracy rate? And how do you do your accuracy rate? Using this testing data set. Because in this case, you already know the answer. So whatever your algorithm predicts, you can compare it to the answer. You don't have to wait for the future. You already know the answer. And let's say if you're doing this, your accuracy rates comes really low than whatever your domain name requires. Not a good algorithm. Go back, restart this process. Maybe you missed a very important variable, you didn't include it. Maybe you had missing data which you didn't include. So for example, in our example, if I want to predict who will donate money to us, and if I would have missed this step, that would have resulted in my prediction being anybody who has zero income, go after them, which would have been not a good algorithm, because it would have failed because those were missing values. So that's something that happens. You get a very low accuracy rate, and that means it's time to go back to the drawing board. Maybe the decision trees you have don't work that well. Maybe you need to try neural network or regression or some other method. Maybe you did not collect data on something very important. So for example, if I'm trying to predict somebody's weight and I don't know their height, I have missed an important variable. So the reason I keep on emphasizing on some of these other things, instead of simply giving you a demo of Enterprise Miner, the reason for that is that I firmly believe that these are just Enterprise Miner or R or IBM Hyperon or Tableau or whatever you're using. These are all tools. How you use them, that's important. And even more importantly, as you have seen, that the first three steps are what the real value you can add to a project. Anybody can learn SAS Enterprise Miner and start using it. It's not that difficult. But what is more important is business understanding, data understanding, and then having a clean data set. So we did this data partition. The reason it says 2 here is because I have already, as a practice, I did it before recording the session. I sort of did this practice run myself. So I'm using the same flow. If I would create a new new diagram here, then it will not say 2, and I can always right click and rename it if I want to, and I can say NW if I want to put my name stamp on it. A decision tree. You guys have already done this step, so I'm gonna go a little fast here. Where's my interactive ellipses for the training one? Excuse me. Okay. Split node. It shows me when I click on split node which variable has the highest log value. The highest log value means that that's the, you can think of it as the most important variable to have the first divide in our data set. So the first one we did was average gift amount, average in last 36 months, more than I think less than 14, more than 14.4. So you know, the darker this line is, the more data is coming from here. If on this side, that's what the line signifies. Then I can split node here and here. You can, if you want, give me 1 second. If let's say you are doing this, it says this is the first one, you can edit rule. Instead of having the 67,700, you can, you know, round it up. And then one more. Oh, maybe I made it 700,000, so 70. Oh, too many. And branch, I might have to delete one. Oh, okay, so automatically. Okay. So instead of going with the default 63,700, you can always edit the rule if you want to. The other thing, and you know, if I say train node, I'll get this big tree, right? And as you can see, as we keep on going down and down the nodes, the data is thinning out. So you can see the line is less and less darker, and I'm following the path of where most of the data is. But as you can see, the count is reducing, so less number of cases, because we are increasing the purity of the data and removing the diversity. Okay. And I should have, let me, closing interactive decision. So I'm going to do it all over again. And I know we have already done this part, but I still wanted to go over this with you. Okay, looks like I have to, it's all there. So let me just prune it. Okay. Okay. So what I want to show you, or what I want to talk here is, excuse me, let's say you said train node, and it gives you this value. So for some, okay, let me, okay, so it gives you this log value, for example, and I know I messed up this decision tree, so it's giving me the limited ones. But my main point is, let's say this is the highest log value, or let's say this was the highest, or so on and so on. If you have some business knowledge about the problem, you have some business understanding, and I know the data is pointing to this, but I know that in future or in a larger data set, this variable is more important. So you can choose that one instead, and that's where you are adding sort of your own business knowledge in creating this decision tree. The other thing about this decision tree is that unlike a neural network, you can see what's happening here. So you can see the first thing we ask people is, how much have you given us in 36 months? If their answer is this side, we go here. Then we ask them, how much is your income? More than 57,000, less than 57. Then we ask, they come here, and so on and so on. And we can ask question and we can make a prediction with an accuracy as to whether they will give us money or not. So decision trees, the reason they are so popular is that you can see the rules. It's very open, transparent, easy to understand. Unlike a neural network, which is like that. So in a neural network, you do your input and you will get your result right away. It's a black box. You don't see anything inside. That's a good thing about decision trees. We see the process, what's happening there. The other thing which I was talking about was this Gini purity, which is a technical term. So our goal with any algorithm is to have high purity, low diversity. So when you start with your data set, like in this case, you have deers, rhinos, ostrich, lion, all in your data set. So if I have to make a prediction that this animal is a lion or a rhino or an ostrich, it's not that easy. I will first ask them, does it have 4 legs or not? It's a yes, 4 legs. So these are not the case then. Oops, sorry. If not 4 legs, okay, you gone. Then I can ask, are you a meat eater, or are you carnivorous or vegetarian? So it's a carnivorous. Bingo. This 3 questions. On the other hand, as the purity of data gets higher, and what do I mean by purity? You're going through these steps. You're asking these questions, and so from here we don't get right away here. You have to ask those multiple questions, but your goal is to reach this high purity, where in most likelihood you have one type of data available. So anything which reaches this point, we can say it's a zebra. And as you can see, it's 1, 2, 3, 4, 5, 6 zebra cases of zebra. Only one. That's hippopotamus, I guess. So this is what our goal is, because now any animal which come here in this sort of, you can say, bracket, we can say with very high accuracy it's zebra, right? We can very easily say it's not a rhino or lion or deer. It will be a zebra. So that's what our goal is. But to reach this goal, and again, I have talked about all these things before in different lecture, we also have to include the speed of the model. So if you have to go through 10 steps to reach here to here, that might not be depending on the domain and how much speed we need, might not be a good idea. So for example, to reach this point, I will ask you how many questions? 1, 2, 3, 4, 5 questions. And again, do we have the time or not, or yes or no? And if I remember correctly, in your previous assignment, you did do 2 decision trees. One was sort of a maximum decision tree, and the other one was with limited number of leaves. And as you saw in your results. Now let me open that. So that was your assignment number 1, and I've already shared the solution with you. As you saw, we were looking at average square error in the fit statistics to compare the two decision trees, and as you can see that even though the second tree with the where we had less number of nodes or leaves was better, but there's not much difference between the error validation rate, which tells you that instead of going with the maximum tree, so this is the maximum, and then you which you should have renamed like that to maximum, and then added another tree and limited numbers of depth to maybe 3 or something like that. There was not much difference. Okay, so that was up to decision tree, and the reason, even though I know we are done, I still wanted to talk about this, was that so that the things tie up together in a better way. So the next part is regression. So let me go to my notes for regression, and before I do, let me look at the results and show you one more. Okay, and our assessment plot. So that's the other thing, average square error. What you should take from this is, if you look at the blue is the training data set, red is a validation one. So as we reach number of leaves 5, we are pretty good in terms of average square error. Is by good I mean is every leaf being added, or as we go more in depth, the average square error is going down. But from this point onwards, as you can see, from point 5 till 10, we didn't have much improvement in the average square error. It went down for the training data set, the blue one, but who cares about it? In the training one, yes, it went down, but when I tested my algorithm, there was no impact. So my main criteria to judge something was this red line, the validation line. So I would say I would stop at this level in my decision tree. I do not need more than 5 leaves because there's no much addition here. Nothing much is happening. Same thing here. You can see it's even more clear with the misclassification rate. I can actually stop right here, or it's slightly improvement, but not much. And okay, so that was the results. Now let's go to regression. Oh, before we go to regression, I wanted to show you one more thing, which was view model variable importance, which is very important. So this tells me in my decision tree which one are the most important variables for dividing my data set. Okay. So right here, and you can convert these into percentages. So this one is 50% variability is explaining once you add this variable with the top variable, 100% variability. This one medium income 48%, but you combine it with this, it only reaches 50%. So they because you're going from bottom like this, starting first 25%, So my model explains 25% of the cases, 26%, 39%, pretty good jump. 40, not much. 42, 43, not much. 47, 48, not much. 50, good. And then the big jump. So that's why this is top ranked, even though you're going like this from the bottom, to see how much more variability is added. So we started with 25%, went all the way to 100%. So that's why this is the most important variable, at least by decision tree algorithm. So you can simply ignore all these lower end variables. They are explaining us something, but in the presence of other variables, we don't need them at all. And even here, like some of these variables don't add anything. 40%, 40.8, 40.9. So we can ignore this one. And some are adding just 1%, you can ignore them. Just to, if we are in a hurry to, in our domain to build the model and so on. Okay. Okay, so let's now get to regression. The thing with regression is that models like regression neural networks are sensitive to missing values. What do I mean by that? If you have to go back again to decision trees, if you look here in the decision trees, in this branches, you can see more than 7.5, less than 7.5, or missing. Again, missing. So decision trees can incorporate missing data and sort of use that as part of its prediction method. So that, that capability to include a missing data, or say either 10 or missing. So what you would say is, if I would say, if your income is more than 50,000, go on the right line. If your income is less than 50,000, or you don't want to tell me your income, go in the left line. So decision tree can do that. Regression will not. Regression will say more than 50,000, right line, less than 50,000, left line. If you don't want to tell your income, you are not taking part in this experiment. It will discard you. So in regression, we want to take care of the missing values. Otherwise, that rows of data will be discarded from the experiment. Okay, so to take care of those missing values before we can do regression, let's take care of those missing values which we ourselves made empty, from 0 to empty. And how do we do that? Where is modify impute? And we are not applying it to decision tree, because decision trees are fine with missing value. So you can do it here, and if you want, you can even pull it from here, or you can even pull it from here, but it's better to hit from data partition. That's where the data is going to all these, much more cleaner way. And let's change some of the properties here. First, indicator variable, unique values from none. Instead of reject them, input them. And there was one more. Okay, this one. This is already by default mean. So we are inputting those unique missing values, and what are we putting in there? We are putting mean values. So let's say for income, if the mean value is 50,000, wherever it will find empty income, it will put mean. If you want to do maximum, so let's say the maximum income in our data set is 100,000, that's what it will impute for all those missing value. Same way you can use minimum, median, standard, some of the other things are available as well. Mean is pretty standard. And let's run it. So if I remember it correctly, it will now impute missing values for income and I think age also had, age column also had 20-25% missing value. So it will put the mean values of age column there as well. Excuse me. Let's see the results. Okay. So the mean for income is 53,000. That's what we used. This was also empty. Gift card mean was 14 and age is 59. And in 1200 records for age, 900 for gift card, 36 months, and 1100 for income. In all those missing values, we have imputed or entered this value there, which means now we don't have any missing value. Okay, now time to get regression, which would be hiding right there. Connect regression there. The good thing for regression, we don't have to change any properties or anything. Right now we are using logistic regression. Why we are doing logistic regression? Because let me open your assignment. The reason we are using logistic regression is because our predictor variable is 0, 1 binary. So if we would have been using this one instead, target amount, which is a continuous variable, remember I have a lecture uploaded on the type of data, continuous, binary, nominal, ordinal, all those things. So since that's 0, 1, we will stay with logistic regression. Run it, pretty simple, nothing, no other properties to be changed. And again, the reason it's 2 here is because I'm using it 1 there. You can right click, change the name if you want to. Okay, let's see the results. And okay. Okay, so I hope some of you have a background in some simple statistics or some data statistics. You understand what p-value is. If not, please refer to your notes. Anything above point, I would say 0.05 is significant at 95% level. If 0.001, which is very good, 99 point some percent. So this variable is highly significant. I think one of the most significant in a model. This is very significant. Nothing else is significant. So these two variables are significant for us because of those, because the p-value is significant. So it's 0.05, 0.01, or 0.0001. So all those threes are significant values in our decision trees. Oh, sorry, in this regression. So what you can say is that where did it go? Median home value and time from last gift is what is impacting whether somebody will donate money or not. Those are the two significant values, and I think that's one of the question that gets asked, that was asked, something like similar in your assignment number 2. Another important thing to see in this, the results from regression are, especially for logistic regression, your odd ratio estimates. And this odd ratio estimate sort of looks at various for example, let's look at this one first, or this one. So somebody, uh, let's say if somebody was a veteran, then his chance of donating money to us is up by, I would say, 0.6%. If somebody has not donated money uh, to to us, or no, I'm sorry, if somebody has donated money to us in the last 36 months, then his chance of giving us money again gets reduced by point, you can say 2%, no, sorry, not point, but 2%. If somebody has given us money at some point, then his or her chance of giving us money now is around 0.5%. The same. Now, how to interpret this results? I'm guessing gender, female versus you. I don't know what was you. It should be M, but let me take my best guess here. In case of female, the chance of somebody donate, if somebody is a female, their chance of donating money to us is 0.3%. But if somebody is a male, their chance of donating money to us is 4%. The reason I said, see, this much is 100%, so 0.3. This much is 100%, so that means that's 4%. So somebody is male, their likelihood of giving us money is 4 times higher than you. I don't know what was classified as you here. So that's another way you can read the results. And again, all this information is there in chapter number 4 handout under the section 4.3, interpreting regression results. Okay, another thing I want to add to the regression model is, as I mentioned earlier, regression model is quite sensitive to missing data as well as outlier data. So let's say if I have income data, and out of the income data of my 10,000 records, 500 have very, very high income. So those are outliers. So that has a very a strong impact in regression, especially in case of regression, which we wanna sort of tone down. And how do we do that? By using something called transform variable. So let me show you how we do that. Modify right here, connect it to transform. Okay. Now look at the variables. Clicking on the ellipses on that. So what I'm gonna do is I'm going to just as a book says, I'm going to select these set of variables which are all related to the gift being given, this particular measurement of when was the last time gift given, how much was the gift, was it in last 36 months overall, and things like that. So I'm just selecting this set of variables, or you can just select one or two. And what I'm going to do once I select those variables is explore them and see how are those, how are they spread over, what is their the distribution of the data under each of those variables. Okay, so you can see the distribution of each of those variables, and except couple of them, uh, most of them are pretty skewed towards one side. That means there are a lot of outliers in the data set. So let's say, you know and just for the sake of example, these are some of the variables which has a lot of outliers. They were skewed, and instead of being default method, I'm gonna change it to, why is not changing it to log? Am I missing? I don't know, maybe let me select one at a time. Okay, I can do it one at a time. So what this log method does is, this sort of reduces the impact of outliers, and whichever variable you feel needs that, you can go and apply that there. And I think all you need to do next is say up okay, and now let's disconnect this connection and connect it right there, and results. So what I just did was, instead of having this direct connection of from data partition to impute, I added this transform variables in between so as to take care of the outliers in certain variables. Then I also, with impute, I took care of the missing values, and now I am running a regression after these two steps of impute was there, these two steps to, again, to do what? Data preparation. And now if I run my regression, it would be, the results would be much better. But again, I just randomly did transform variables, so my results would not be that good. But just wanted to show you that from especially for your assignment viewpoint. Let me see if there's anything else in your assignment which needs for me to I think the other thing you will do in your assignment is something called stat explore, which is under explore right here, which simply means exploring the data. It just provides you a little bit more options and a better view of, as the name implies, exploring your data sets and giving you some of the descriptive analytics. Let's let the results come and I'll show you. So that is the results from your stat explore, variable worth, and you can see things like that. You can make different plots, summary statistics, and all those things are available there. Okay, so that is regression. Now I'm going to move to the next part, which is neural networks. And the thing with neural networks is that it is we have, at least in this case, we have done all the groundwork with transform variables or an impute. Let's say you were not doing regression, so you were, let's say, moving directly to from decision trees to neural networks, you would have to do this groundwork for that as well. But now we do not. So life is good and simple. Just go to model. Where's the neural network? Which one I need? Just grab the neural network. Oh, why didn't it come? Actually, I need this one. Sorry. connect it to impute, and I think I have to change. Is there any setting? Nope, no. Any setting for that? To change under train. I think under optimization, just one setting I have to change, which is we are not doing any preliminary training. We are right away using just our data set for one simple training. Run the results. So it's pretty simple. It's a black box. You just bring it, connect it to your data. We have already done the groundwork, and now we can see the results for those. I was taking some time to run it. Results. Those are some of the results. Let's just look at some of the plots. Assessment. I want to look at. Oh, it's right there. Average square error. Oh, looks like neural network is not that good for us. Till this iteration around 7, this error was going down, and we are doing good with the training data set. But look at the error; it goes up. So just stop here. No need to go further up. Misclassification rate, same story. Number of wrong classification. So that's the point to stop. But my guess is that neural network might not be a good fit for the problem we have. Plus, on the other hand, I just randomly applied log to some of the other variables, so that might have caused the problem as well. So I'll stop here. But if you want, the next week, we are simply doing model comparison, where you do this, and this, and it compares your model. And you run it, but I will explain to you the results and talk more about it in the next weeks. So let's see the results. Excuse me. That's okay. It's going to take some time, but that's for our next week. So all the best, guys. Hope you won't find assignment number 2 quite long. I've combined both regression and neural networks together for this assignment too, and because the reason for that is you've already done all the groundwork, so it's all about just connecting one more node and running it.